All right, so welcome everyone. As I said, we are going to take this week a closer look at the differences between supervised and unsupervised learning. And then once we go through some of the kind of theoretical aspects of that, we're going to switch gears a little bit and look at some methods of how to work with larger data sets. As I said, we're going to do a little bit of language detection using Butter, that tool we worked with last week. And then we are also going to do network visualization using a free open source tool called Gephi as well. This week, we are still going to stick with out-of-the-box tools that don't really require any programming experience. Next week, in our final workshop, we will learn a little bit of Python as much as we can within the period that we have. And we will try to, better understand how we can do AI and other computational tasks with a bit of programming. But today, we'll focus on using out-of-the-box tools as we did last week. But before we look at some of those tools, I wanted to talk a little bit more about machine learning. So machine learning falls into two broad categories: supervised learning and unsupervised learning. So supervised learning really requires labeled data. These are data sets that are designed to train algorithms into classifying data. So for example, a classic example is determining whether an email is spam or not. And so essentially, you would use a supervised learning approach because you would provide emails that have been labeled as spam or not. And we'll go through specific examples of both supervised and unsupervised learning in a minute. Unsupervised learning is a little bit different in that it uses machine learning algorithms to analyze and cluster unlabeled data sets. These algorithms essentially discover hidden patterns in data without the need for human intervention. And we'll go through some more examples of both in a minute that'll make this both ideas come a little bit clearer. So within supervised learning itself, there are two broad types of supervised learning: regression and classification. So the difference essentially is that classification will predict a category. So for example, with our spam detection, it's whether to spam or not, or for example, whether somebody should receive a loan or not. So it's a category. Where regression essentially, regression supervised learning approaches are trying to predict a continuous value. So something like a stock price or a temperature or the amount of rain in a given day. That's an example of a regression-based supervised learning problem. So with supervised learning, we want to figure out some features or characteristics that help us predict a value. So again, in the case of spam, whether it is spam or not. These features essentially are something that we can measure or a characteristic of a specific phenomenon. So another classic supervised learning problem is trying to predict the sale price of a house based upon its features. And I wanted to ask all of you, what are some of the features of a house that you think would determine its value? And again, as we did last week, I'd like to use Poll Everywhere to do that. So if you go to this URL here, so pollev.com/AITMU with your mobile phone, or perhaps you can open up another browser window, you should be able to submit a response. What are some of the things that you think determine the sale price of a house? I'll give you a little bit of time to do that. Lot size, location for sure. The square footage is obviously a very big one. Lots of examples for location. Parking, for example, in Toronto might be another one. So if you have parking or not, that will obviously increase the value of your house potentially. Whether it is new, the age of the house for sure. Bedrooms, bathroom numbers, school zone for sure. All different features that might determine the sale price of a house. Thank you, everybody, for submitting. And so if we look at these features, I guess, in a little bit of a table, we can get a better example of how we can use these forms of features to help perhaps predict the value of a house. So with supervised learning, we can take labeled data that we have and use AI algorithms to predict what that price might be. So you can see here, in this example, we have used square footage, we've used bedrooms, the amount of bedrooms, the amount of bathrooms, whether it has parking, and dependent on all of those values, you will get a specific price. So in this example, we would use historic prices so that we, for example, know that this 1,200 square foot house with 3 bathrooms or 3 bedrooms, 2 bathrooms, and parking, sold for 900,000. And you can see some differences. So, for example, as the size gets larger, it gets a little bit more expensive. And whether it has 5 bedrooms and 4 bathrooms. And so a supervised AI algorithm can learn from this data and understand what features might impact the price of this house. So this is an example of a regression model because we are trying to predict a continuous value. So this value of price could be 900,000 or it could be $900,001. It's a continuous model. So here's another example of a supervised learning problem. So will it rain? So this is a simple problem. We're essentially trying to determine yes or no whether it will rain in a given day. And we have a variety of features. So we have a date, we have a temperature, we have the wind speed, and we have the atmospheric pressure on that day. And again, these are historic examples that have, on this given day, it rained and these features were present. So this is an example of a binary classification problem as we are trying to predict a specific category, whether it'll rain, so yes or no, rather than a numeric value. And because it's binary, it has 2 potential options, yes or no. A multi-class classification problem could have multiple options. For example, if we were trying to determine or predict the species of a particular animal, it could be, for example, a dog, a cat, a goat, a sheep, etc. So there are multiple options. So the rain example is binary because there is 2, but you could have a classification that has more than 1 option. Here's an example of a unsupervised learning problem, and it's a common one where you're trying to group customers into logical groups. And what these algorithms will essentially try to cluster them together. So we will take the features of our customers. So we have, in this case, age, their income, their education level, where they live, and perhaps the amount of money they spent at our store. And then we will try to cluster them together. Well, the algorithm will. So clustering is not the only type of unsupervised learning, but generally all of these approaches surround analyzing unlabeled data. You can see here, there isn't a label per se connected to this as there was before. And we have a variety of features, so age, income, education, location, and the amount spent. So when you often feed this form of data into an unsupervised learning algorithm, you will often end up with a diagram somewhat like this, where you have your different customers. Each one of these squares represents a particular customer, and then you can logically group them together, or you can allow the algorithm to do that for you. And so looking at this result, you can see that these people, because they are in this graph near one another, can be grouped together. And similarly, you can do the same with the white grouping here and the green grouping as well. So essentially from this diagram, you can see clusters of customers that can be put into logical groups. So let's maybe try to sum up some of the differences between supervised versus unsupervised learning, as you can see with this table. So as I said, one of the main differences between supervised and unsupervised learning approaches is the fact that supervised learning requires labeled data, where unsupervised learning does not. It is focused on unlabeled data. So supervised learning learns from the training data and adjusts itself to try to understand the correct answer. Supervised learning is often more accurate, but requires more human intervention in that you will have to have a data set where all of your values are labeled. And so you have to go through, each one of these days and ensure that it's labeled as yes or no for rain, or you have to know the price of the individual houses. So it requires theoretically more human intervention than unsupervised learning models do. Unsupervised approaches work to discover the structure of unlabeled data. It still requires, though, human intervention to validate the results. And we saw that a little bit last week when we looked at our example of topic modeling. Topic modeling is an example of an unsupervised learning technique. And we got groupings of words, but we needed to, use our human intelligence to determine what the topics were. And so neither one of these doesn't require some form of human intervention. It just, I think, at least occurs at somewhat of a different stage. So essentially, that is the main differences between, and there's more here on this table, between supervised and unsupervised learning. So an obvious requirement of any form of artificial intelligence or other computational research is data. And this data can come from, obviously, a variety of different sources. So this could come from documents, and we saw this when we tried to do topic modeling on our obituaries from the New York Times, as we did last week. It could perhaps come from user responses. So if you've collected user survey data, you can use that as data for your artificial intelligence work. You can also obviously get data from web-based APIs or application programming interfaces. And so when I'm going to be using a lot of Twitter examples in this week, and we did a bit last week as well. And those were taken from the academic Twitter API, and essentially a way that you can programmatically get information from web-based spaces. And we'll talk a little bit more about how you can do that next week when we touch on Python. And you can also get them from open data repositories. So more local governments, including here in Toronto or StatsCan, for example, are putting their data, their results into open data repositories, which you can then download and then use for AI or computational work. And so there's a variety of different sources for getting data at this point. One of the important aspects of working with data for AI or computational uses is that this data needs to be relatively clean, meaning that it follows a relatively standardized format. In the case of supervised learning based AI approaches, this data, as we saw, also needs to be labeled. Particularly for AI solutions, it's often helpful to have a significant volume of data as well. So the more data you have, the better the algorithms can learn from it. So, for example, when we're thinking of that example of what is spam and what is not, the AI models need to see a significant amount of labeled data to understand, for example, what words might be indicative of spam. So, might have certain words or certain URLs that are typically occur within spam emails. And the more of that you have, the easier it is for those AI algorithms to determine, to make that prediction. Before we go into some of our demonstrations, I also want to talk very briefly about AI bias. So AI bias is obviously a very significant topic, and we're only going to be able to talk about it briefly in this workshop with the time that we have. But I essentially wanted to get across that AI models and the software that often is used from them are often human-made. As such, they are often instilled with the racial, gender, and other types of stereotypes and prejudices that will also occur in society. So I wanted to go through a couple of different examples of, I guess, some of the problematic aspects of using AI or computational approaches. And so this first example is based upon research out of McMaster, and I'll share this. This is an article from Nature. I'll share it in the chat. But essentially, what these researchers found is that when they used a very popular text generation tool called GPT-3, and when they the way the GPT-3 works is that you put in a text prompt and it responds based upon its language model that tries to kind of complete your conversation for you. And so these researchers put in the phrase, "two Muslims walked into a bar." And when they put this in 100 different times, those same words, GPT-3 consistently returned completion phrases that were violent in nature. Meanwhile, similar questions using other religious affiliations returned dramatically lower rates of violent references. In this case, GPT-3 was reinforcing stereotypes against a particular community. Another example came from, and these are only three of many, many examples. I'll share it here as an example from a investigation done by ProPublica, which is a nonprofit news organization in the United States. And what they found essentially was that machine learning approaches were being used in the States to determine whether individuals were either fit for parole, and they were also being used to assess risk scores for reoffending. And their study determined that these algorithms were racially biased against Black people. They were denying parole, and were assigning higher risk scores against Black individuals. And part of that was because of the biases of the underlying data set. And again, the ProPublica link that I shared there in the chat provides far more information. And finally, this was another study from the University of Washington. Again, I'll share this link, where they were studying the impacts of when you, for example, did Google image search and put in who is a CEO. And the interesting thing is that they did this study both in 2015 and tried it again in 2022, and they found that not much had changed. In most cases, the image results that they had returned were mostly white men. So it was interesting over that time period that there wasn't much change in the image results. And again, you can look to that study for more information about that. And so again, we're just touching on things very briefly, and we will address questions again, as I mentioned at the beginning, after we're done. But obviously, AI and algorithmic bias is a very large topic, and we don't necessarily have enough space to adequately explore it here. But I just wanted you to be aware generally of the limitations of AI and computational approaches. AI and computational-based tools are not necessarily without bias. And as researchers and workers who might use these AI-based tools, we need to be aware of the limitations of these tools and be cognizant of the potential harms that these tools may cause. And we can talk a little bit more about those issues in our question and discussion period a little bit later on in the workshop. So switching gears again, I wanted to now look at some AI-based tools. So we're going to do another quick example using Butter. Essentially, we're going to do a simple supervised learning technique using Butter. And let me try to mute all the waiting room sounds here. So we're going to do another simple example with Butter. So if you want more information on Butter, our website has the video from last week. But we are going to try and look at a data set of Twitter conversations related to Central American migrant caravans. This data set has over 100,000 different tweets within it. And this data set features multiple languages. Much of it is in Spanish, but occasionally there are other tweets that are English or in other languages. So if we want to do analysis for potentially only on the Spanish language texts, we need to figure out a method to identify which of these are Spanish and which of these are not. With a data set of this size, with 100,000 tweets, it could be relatively time consuming to manually label all of these tweets. And this is essentially a great problem to solve using supervised learning techniques. And this is essentially a multi-class classification problem, as we have several languages that could be represented in our data set. So we could have English, we could have Spanish, we could have French, etc. So it's more than one, more than two, so it is not binary. So Butter essentially has the functionality to identify the language of the text. So this functionality really relies upon pre-trained language models, and which obviously begs the question, what are pre-trained language models? So this is a definition that was provided by NVIDIA. AI and machine learning models are built on algorithms and are trained using data and human expertise. These models help us accurately predict outcomes based on input data such as images, text, or language. But building, training, and optimizing production quality models is relatively expensive, requires numerous iterations. You have to have certain domain expertise, and often requires countless hours of computational resources. Pre-trained models help us in this respect, in that they have been trained on representative data sets and fine-tuned with different weights and biases. These models can be then easily retrained with custom data in a fraction of the time that it takes to train models from scratch. So again, that was from NVIDIA. But for me, pre-trained models are essentially AI models created by someone else that allow us to solve a similar problem. They are nice because we don't necessarily have to go through all of the complex effort to train an AI model ourselves. So again, here's the problem that we're trying to solve. So we are trying to identify the language of tweets. And we have this data set of 100,000 or so, I think it's 110,000 of tweets related to the Central American migrant caravans. And we are going to use Butter and a supervised learning approach available in it to do language detection on this data set. So this data set is similar to the Twitter data set that we looked at from last week. I'll just look at it very, very quickly. We essentially, and this is probably quite small on your screen, but we have 100,000 tweets with IDs, a date when they were created, and the actual tweet text itself. And we are essentially going to use Butter to determine the language of this tweet text. And this is a CSV file. So as we did last week, we were first presented with this Butter screen. We will launch Butter. It takes a second to launch. I'll move it over here. And as before, and again, if you want more information about Butter, look through our videos from last week or the longer form video on our site as well. But we have essentially 3 areas of Butter. We have the available plugins to do work. We have information on the plugins over here. And then we have your analyst pipeline here, which is essentially the steps that you will do to do the analysis that you're trying to do. So as last week, our first step is going to be loading a file. So we will go through our sequential plugins. We will go into the category for load files. And in this case, as last week, we are also going to read text in from a CSV file. We'll click on the button to add this plugin to the pipeline. We will then highlight it, change the plugin settings, and we want to find the specific file that we want to analyze. So it's on my desktop. We will choose the CSV file, and we'll keep all of these formatting options here because it is separated by commas, and the data is contained within quotation marks. But as before, we also have to specify a unique row identifier. And in our case, it is an ID, which we have from our Twitter data set. And then we have to select the data that we want to do our language analysis on, which is our tweet text column. So both of these columns here are essentially the columns that are represented in our CSV file. And then everything should be okay. So we'll just click OK. And then our next step is that we want to do our actual language analysis. So we will go to the plugin category for language analysis. We will click on identify text language. We will now add it to the pipeline. That moves it again from our available plugins over to here. There's a few plugin settings you can play around with this plugin. If you want more information about how it does it, it's available here. But if you click on plugin settings, you have a couple of different options for a pre-trained language model. We are going to focus on the core 14 language models because it's relatively quicker. We're trying to simply identify between Spanish and English. If we wanted to try to determine more languages, we could either use a 82 language model or a 280 language model. But I found with this example, the 14s worked better. But again, if you had more languages represented in your data set, these other ones will work well. The one thing I found when I used the 82 languages, there was some regional dialects of Spanish that were discovered within that as well, which might be important depending on what you are doing. But the more languages you have, the longer it takes for this pipeline to complete. And so using 14 languages makes it relatively quicker and works well for our case. So we'll just click OK. And then finally, we obviously want to save that data somewhere. So as we did last week, we will go to save output files. We'll save this output to a CSV. We will move the plugin to the pipeline. We will click on the plugin settings again because we have to specify what we want to have. I've already saved it, but we'll do another version of it here, depending on how long it takes. Just give it a name and then go OK. And then essentially we have, as we did before, we had all of our steps available. So we will just click on begin analysis. And this takes a little bit longer because it's a little bit more processor intensive. I have an example, results example already open here. Depending again on the number of tweets you have in your data set, it could take a couple of minutes. And this, again, the 14 or the 13 language model was relatively quicker. But essentially when all of this is done, it's probably still going in the background. Oh, it's almost done, 50% done. You'll get a spreadsheet or a CSV file such as this, where essentially you will have the ID of every tweet, and then you will have the language that it is determined from every tweet as well. And it uses two different approaches that we won't go into, but naive Bayes and a ranked choice approach. But you can now it's finished, so it took a few minutes, but you can now essentially see that every single one of our tweets has been labeled. So most of them are Spanish, but you'll see a few other examples here, like Italian. There are some English ones, Portuguese as well. And in this case, what it's doing is giving you a the ISO language code for the specific language. And depending on which one of the models you use, it will give you a different language code. So you just basically essentially refer, this is a Wikipedia page for all of the ISO language codes. But essentially now we have a data set for identifying all of our different, the language of all of our different tweets. And we would then be able to kind of filter our tweets if we, for example, wanted to do analysis only on tweets of a specific language category. So again, this is a relatively simple, sorry, let me set this up. This is a relatively simple unsupervised learning, supervised learning technique that Butter allows you to do. And essentially, we're using a supervised learning approach to identify the languages of our data set. And again, I'll go through any of the remaining questions when we're at the end of our workshop period. So again, that's a simple way to use Butter to use supervised learning to solve a problem. So let's try and tackle another type of problem using AI and computational approaches using the same data set. So again, this data set surrounds the migrant caravans that were occurring through Central America through the last 3 or 4 years. And so we essentially have a problem where we're trying to analyze who are the significant influencers within this data set. And so how do we solve that? So we obviously would solve it with network visualization, and that's what we're going to do using an open source tool called Gephi. So what is it? So network visualization obviously is a form of network analysis. Network analysis allows us to examine the relationship between different entities. It's often used for social media analysis, as we are going to do now, but it can be used for other forms of relationships, such as, for example, research collaborations, peer networks, email communication. So network visualization is essentially the visual representation of our network analysis. And this is a relatively simple example of a network graph. We have essentially nodes, which are the little circles, and we have edges here. So network graphs consist, as we see, of edges and nodes. Nodes represent the objects of interest. And so the case of our Twitter data set, it would be Twitter users, while edges represent the connections between them. And again, through the example that we're about to do, that would essentially be, how they are replying to one another. And so we are going to visually represent how people are responding when they communicate with one another using a certain hashtag. And that's what those edges represent. So an edge would essentially represent, this person communicating with this person. These graphs can essentially be directed or undirected. So for directed examples would be, for example, when somebody phone calls you via a phone. So you call someone, it is directed. I'm making the call towards you. That is a directed type of network relationship. Can also occur in Twitter, where you follow someone, but they don't necessarily follow you back. So those can be directed. Examples of undirected networks can include computer networks, also Facebook as well. So when you friend somebody on Facebook, you become mutual friends. And so again, there is less of a directed notion to it. Here's another example showing, this is an example essentially of 4 different people. Let's say there are 4 different researchers and they all are citing one another's work. So we have Bob, Mary, Selma, and Frank. So essentially you can see here that Bob, he hasn't cited anyone. So there is no edges going from him to other individuals. You can see the directionality based upon the head of the arrow. But if we look at Mary, Mary perhaps has cited a work of Bob. So you can see that this edge is directed towards Bob and represents that relationship. Selma has cited both Bob and Mary. So again, you have directed edges between both individuals, while Frank has only cited Mary. So again, we have a directed edge between Frank and Mary. And this whole kind of grouping of individuals, these nodes and edges, represents a network visualization of how these individuals might be communicating with one another, in this case, using citations. So this last graph was obviously a very simple graph. We wouldn't necessarily need any computational tools to help us create a graph like this. We could do it pretty easily by hand. But what happens when you're trying to analyze social media commentary? As researchers or workers looking at a particular hashtag-based conversation, you might have hundreds of thousands of different tweets within your data set. So this is where computational tools that may or may not use AI or other computational approaches can really help. So I wanted to show you one of these tools, Gephi. And so Gephi does a lot of things, and this is going to be a relatively quick overview. Again, we have a longer video of me going through Gephi in far more detail on our website, which maybe we can share that URL again. And Gephi does a lot of things. And so we're going to focus on the network visualization aspects of Gephi, but it does a lot, and it is a really great free open source tool. And we're just going to touch on the data visualization aspects of it. And so we are going to do data visualization on the same data set we looked at a second ago, which is our migrant caravan data set. And so again, we have a variety of people talking about this issue using the central, there was one central hashtag migrant caravane. This data, as I mentioned before, was acquired using the Twitter API. And I, as a researcher, want to try and get a better sense of some of the main influencers within these caravans and get a better understanding of how, this network of people might be talking about this issue. And so to use Gephi, we essentially need two types of data files. We need our nodes, which in this case, as I mentioned, is our Twitter user IDs and their corresponding Twitter handles. And we need a file of our edges as well, which essentially are the source and target of our tweets. And so let me show you the data set quickly here. So we essentially have a node file here. This is a CSV file just opened in a text editor, but we have a CSV file that essentially has every single participant in our Twitter conversation. So their user ID and their Twitter handle. And then we have a second file of our edges, which essentially is the source. So the person who is doing the tweeting, the target, which is the person that they are tweeting towards or applying to, which is this ID here at the end. And then we've also included the text of the tweet as well. We wouldn't necessarily need that to do network visualization, but it can sometimes be helpful because you can do a little bit more analysis and get more detail in your graph if you also include other information such as the tweet. But the required elements are both the source and target. And when you provide, and one of the challenges with doing network visualization is that you have to prepare your data set in this format. And so you can use a tool like Excel to potentially get a unique list of all of the participants in your network conversation, or I use a Python-based approach, which we will touch on a little bit next week. But the key requirement is that you need a list of nodes, so your conversation participants, and then you need a list of edges, so those connections between your participants. So we have those two CSV files now prepared. Again, CSVs are comma separated files. So this is Gephi. Gephi is a free tool. When you first start it, you get this kind of welcome screen, but we will close it. And so the first step when you do any form of work in Gephi is to start a new project. So you would go to File and then New Project. And essentially, it changes the view a little bit, but it'll open a little workspace here, which you can see here within this tab. You can have more than one workspace, but we're essentially going to do all of our work in this particular workspace. And so the first step to do network visualization is to import our data into Gephi. So to do that, you go to this little data laboratory button and you click on it. And so we are now going to essentially import the data that we just looked at. I find it most helpful to import our nodes first. So we will just go to import spreadsheet, click on this little button, and then we will find our node CSV file, which is on the desktop of my computer. We will open it and we'll keep the settings mostly as is. It gives you a little representation of, I think 100 or so rows of your data set. You want to make sure that it's importing it as a nodes table. It should do it as default, but you just may want to double check. And you can also set the character set, which in most cases will be UTF-8, but if you're doing work in other languages, it may be different. So otherwise, our data is comma separated. So we'll keep things as is, and then we'll just click next. We can specify what columns we want to import. So you may have extra columns within your data node data file, and if you don't want to import them, you can select them here. But in our case, we want both because we want the user ID and we want the label, the Twitter handle of our individuals as well. So we want them both. We'll just go finish. The only thing I will change here, you can see that we have 34,000 different nodes, so 34,000 different distinct users. I go through more of what's happening here in the longer form video, but essentially what we want to do is append this to our existing workspace. If you didn't switch this from new workspace to append, it will create another little tab up here. So then we'll just go, okay. So now we have all of our nodes, and you'll essentially see a list of all of our different participants in our network conversation, as we saw before when we looked in the CSV file. So that is our first step done. But if we want to do network visualization, we need more than just the names of the individuals participating. We need to know the connections between those individuals. And so we do that by importing in our Edge file. So again, click on Import Spreadsheet up here. We would then look for our Edge CSV file that we've pre-prepared. We would click on it and go open. It's a similar format. You just want to make sure that Edge's table is highlighted here instead of the nodes. Click Next. Again, in this case, similar to what we saw before, you can specify what columns you want to import. In this case, we want them all because we do want to include our tweet text as well. But you could have other columns that you don't want to. You can see here that, again, the source and target are grayed out because in this case, they are required. So we will go finish. We will again switch this to append to an existing workspace. Your graph types can be directed or undirected with Gephi. In this case, we will keep it as directed because we know that our tweets have directionality to them. And you get more information about the differences, the number of edges and things like that. So otherwise, everything is good here. We'll click OK. And similarly, we will see all of our, if we switch from nodes to edges, we will now see all of our edge data. Sorry, we'll see the source, the person who is doing the tweeting, and who they are trying to reply to. And you will also see our Twitter data here as well, so the tweet data. So essentially, we now have the beginning stages of our network visualization. We have all of the data that we need within it. So if we now go to our overview button here at the top, this will show us an example of our network visualization as it is now. And you can see we have this relatively not useful big black square. Essentially, if we zoomed in, and I'm just zooming in by scrolling the middle mouse button of my mouse, you can see this is a whole bunch of little tiny dots, all kind of condensed into one giant square. And this obviously is not particularly useful. It doesn't, all of our nodes and our edges are represented, but we can't see them at all. So one of the most powerful aspects of network visualization and Gephi is to do some type of layout algorithm on this data to make it appear more visually appealing and more meaningful. And I won't have the time to go through all of them, but a common one that is used for network visualizations on social media data sets, particularly large ones, is Force Atlas. So you see here on the left-hand kind of column, you have a layout section. We have a variety of different layouts to choose upon. We will choose Force Atlas 2. And there's a couple of different settings you can play around with. But let's just leave the settings as is for now, and we will press this little run button. And you will quickly see, and I'll zoom out a little bit, our network visualization take a little bit better shape. And so you can now see things kind of breaking out. And if we zoom in a little bit, you can see the individual nodes and some of the connections between them far better than you could before. And that's, again, because we've applied this Force Atlas algorithm to this data set that we had. And so essentially with all of these algorithms, they'll essentially keep running until you press stop. Eventually, when it appears to be changing a little bit less, I will generally press stop. And so now if we zoom in again, we can see the network visualization a little bit better. For example, we can see if we zoom in the individual nodes, and we can also see some of the directions between them. So in this case, this dot represents a user, a Twitter user, and they have replied to this individual here. And so not bad at this point, but there's still some other changes that we can make to make it look a little bit better. And there's some features essentially within the layout, the Force Atlas layout, that allow us to make things look a little bit better. We still see a lot of overlap here between our different nodes, and it's challenging to see some of what happens in some of these larger clusters. So we can do a couple of things within Force Atlas to help with that. There is a setting here for preventing overlap. If we click on that and then run it again, they will break out a little bit more, and we'll press stop. We can also do scaling as well. Scaling essentially determines how much repulsion you will get from the center. And if we change it from 2 to perhaps 10 and press run again, you can see it's breaking out even more. So things are starting to get a little bit better. We can press stop to stop that. Now, these once you do these features, they operate similar to the larger layout atlas as well, so that they'll keep going until you actually press stop. So again, we have a somewhat interesting network visualization here now. We have a variety of different nodes and edges, but we can do some more formatting based upon some network statistics that might make this even more visually appealing. And so right now, every single one of these nodes is exactly the same size. And this graph could be more useful if we had the diameter of these individual nodes changed based upon how influential these individuals are. So there's a lot of different ways or statistics that you can use to measure, influence or different network factors. And we are just going to use a relatively simple one called degree, which essentially will determine how many individuals are, if this, the amount of times that this person is either replying to somebody or being replied to essentially is their degree. So if they've replied to different people 5 times, they have a degree of 5. And so essentially the higher the degree they have could be a relatively rough indication of how, how meaningful or how influential, or at least how active they are within a conversation. And we can do a simple calculation on this graph and then have these nodes changed based upon that degree. And to essentially do that, you have to run a couple of different statistics. And the statistical calculations are all kind of listed here on the right-hand side in this column. So you can run any of them by clicking on the little run button beside them. So just make sure you have the statistic tab highlighted and click run. So you get a little report and essentially what it does is calculates the degree of every single node within your data set. So it is now calculated how many kind of replies occur for each one of these users. We'll do another one as well called modularity, which can be helpful to split this graph into a different community size as well. So we've done that one. So essentially, once we have done these network, maybe we'll do this network diameter one just for fun. We'll go, okay. So now that we've done these calculations, we can now change the appearance of our graph based upon these calculations. You can see this one takes a little bit more time, so it's calculating here in the bottom. So if we wanted to change our node appearance, we can again go back to the left-hand side of our screen on Gephi. And what we want to do is focus on the appearance of the nodes within this section. And we want to change their size. So that's this little icon here, which seems to be a couple of different concentric circles. If we click on that, we can change the size. And we want to go from it gets a defaults to this unique tab. We want to switch it to ranking. And then essentially what we can do is we can choose an attribute to base the size change on. So because we've done those statistical calculations, we can do one based upon degree. And you can specify whether the range of size you want for the largest and smallest, but we'll just keep these as is. So our smallest degree will be 10, our largest will be 100, and we will click apply. And when we do that, you will kind of quickly see the graph change. And so it's still a little bit challenging to see, but we essentially now, the higher the degree, the larger the amount of the diameter of the circle is. We could maybe do a few more things. Let's change this to 30, the scaling to 30 to maybe see a little bit more separation. And you can now see that this particular node here is a particularly active node within our Twitter data set. A lot of people are replying to this individual, and this person could be replying to a lot of different people as well. And is now helpful because we've had these nodes changed based upon the size of the amount of degree that the amount of back and forth replying that these individuals do. Another helpful technique that you can do as well is labeling these nodes. And so we have a lot of circles here, but we essentially don't know who these individuals are. And so we can get a sense, this is probably a particularly influential person, but by just looking at the circle, we don't know who that individual actually happens to be. And so when we imported in our node data set, we also included their Twitter handle, and we can include that handle in our network visualization as well. So we can do that essentially by clicking on the little T here at the bottom. And you essentially now, and this is very, very garbled, but you can essentially now see the Twitter, and we can zoom in on one. You can essentially see the Twitter handle for this individual node kind of overlaid on top of that actual node. And so we'll do a few more things to make this obviously more visually appealing. We can first maybe change the size. We can play around with the size a little bit. We can do it here, I think. Just slide it down. We'll make it a little bit smaller so that the text doesn't take as much space. But we can also, like we did with the nodes, we can have the text size changed based upon the degree size as well. So it's hard to see, but there's a little A here at the bottom, and we can change it to the node size. So essentially, the larger the node, the bigger the text will be as well. And obviously, we have currently the node the same color as the everything is black here, the font. So we might want to change the color of that as well. So maybe we will choose a font that, let's do pink or something that stands out a little bit more. So we can now, this visualization is a little bit more useful now. So we can see who this actual node is a Twitter account of a film production company in Central America. And we can see by just looking at it that it is we now know who each one of these nodes are. And so if we were using this to get a sense of who the influential people are, this provides us far more context than if we were just looking at the dots. We now know who the individuals are. One last thing I want to do, and again, I go through far more detail in the actual recorded video, is that Gephi can separate this whole network visualization into communities as well. And so when we did that modularity statistic, it was using a algorithmic approach to try and determine, some communities that each one of these nodes would be in. And so we can change the color of our nodes based upon those community calculations. And again, we can do that in appearances. If we switch to this it looks like a little color palette, and then we switch to partition, and we choose an attribute as we did before, and we will do it based upon modularity class, which was made available because we did that modularity statistic calculation here. And we'll see now that what it essentially did when it made those calculations is it separated all of our nodes into particular communities, and then we'll assign a color to it. And you can play around with these colors if you'd like. But essentially, when you click apply, all of our network graph is now segmented into different communities based upon these colors and the connections between them. And so we can see that there is a community of participants surrounding probably this production company, but there's other ones as well. So there seems to be a community here because they all share the same blue color. And then you hover over it, it kind of highlights the colors. And then we can see there is another community here surrounding this individual tweeter as well. So again, you can use Gephi to get a far better sense of, how your communities are connected to one another and how they might be communicating with one another. And again, for far more information, like this was a very abbreviated outline of Gephi. Visit our website for the longer form video where I go through things a little less quickly and with a little bit more detail as well. So, but I really find that network visualization and tools like Gephi give us a better sense of what is going on than what we could do manually. It allows us potentially to open up more venues for research that might not have been possible. So we know from this network visualization that that particular film company that we looked at seems to be influential within our data set. And we could, for example, use that information to focus our research on that community. And that wouldn't have been possible without using some form of visualization or statistical technique. So that's essentially the basics of network visualizations and the basics of Gephi. Again, Gephi is a very great tool, and it is a free tool, and it can do quite a bit more. And if you have an opportunity to check it out, I would definitely encourage it. And if, again, you want to watch our longer form video related to Gephi, and there is a link to it on the site as well, visit our website at torontomu.ca/AIDA.